handful of technologies have radically changed the course of human history. The combustion engine, the microchip, and the internet created massive shifts in what humans were capable of achieving. The next big breakthrough is coming, and it's going to be bigger than all of those combined. But it's making some researchers very nervous. That potential breakthrough is self-improving AI. In this video, let's take a look at some research papers that seem to suggest that AI is not far from being able to bootstrap itself. In the last few years, we've seen AI models rapidly improve their skills and abilities. But those improvements are driven by human ingenuity. Humans come up with new ideas, new experiments to try, and new code to help models acquire new skills. Not that long ago, 100% of AI research was conducted by humans alone. Humans could improve AI. AI could not improve itself. But that's slowly changing. If we see this trend continuing, at some point, the AI will be better at improving itself than humans ever could. And this is where it gets a bit dicey. A different way of thinking about it is that the smarter that the model gets, the smarter it can make itself. The growth is compounding. It's exponential. A blog called Wait But Why posted this in 2015, and I think it illustrates the point pretty well. We're standing at a train station called Human Intelligence, and we're waiting for the AI train to pull in. And as it gets smarter and smarter, it gets closer and closer to us. We expect that there's going to be some moment where it arrives at human level intelligence. But what's this? It's coming in kind of fast. Is it not going to stop? Nope, it blows right past us and it just keeps going, accelerating exponentially. And it's kind of hard to imagine what this is going to look like. Imagine a chart where intelligence is ranked and humans, dogs, and ants are all basically clustered around the same area. And then much, much higher on the scale is another form of intelligence. What does that even look like? That intelligence is also a step function. Just like the ant can't even conceive of human level capabilities, much less do them, we can't even conceive of an intelligence that's 5 to 10 steps above us. Now, all of this is just science fiction at this point. This is just theoretical, and we have no idea how this is going to unfold. But we are seeing the early versions of AI already improving itself. Let's take a look at a couple examples. Voyager. The first is a project out of Nvidia, and this is a team that's behind a lot of really great work. Dr. Jim Fan, Anima Anand Kumar, and their team, and I'll link that paper in the description. They decided to see if they can create an AI bot that can play Minecraft. The project was called Voyager, an open-ended embodied agent with large language models. Now that was not the first project to create a bot in Minecraft, but this one was not like any that anyone had ever seen before. First of all, this brain behind the bot was not a script coded up by one of the researchers. It was GPT-4, the model behind ChatGPT. It was told that its ultimate goal was to discover as many diverse things as possible in the game, accomplish as many diverse tasks as possible, and to become the greatest Minecraft player in the world. It was given a set of guidelines and instructions, but keep in mind that these models have a context length limit. The instructions amounted to a few pages of guidelines in English. Now, at the time when this was published, ChatGPT did not have the vision mode yet. It couldn't see, it couldn't look at the screen. So how was it able to play? Well, they used an API called MindFlayer. This allowed it to get information about its surroundings in text form. The API gave it information about its health, if it was next to the river or surrounded by snow. It would tell it what time of day it was, etc. Also, it allowed you to do normal player actions like moving, mining, picking stuff up, and if you're my 5-year-old nephew, spawn billions of octopi in a tiny pond the size of a bathtub. So at every interval, ChatGPT would get a bunch of text telling it about its environment, and it would have to answer with the action that it needs to do next. For example, if the input is you're next to the river and you're hungry, it might suggest that you fish in the river. If you are under attack, it would suggest that you defend yourself. And when possible, it would advance its global objective to become the best player in the world at Minecraft. And it would do this like how any other player would. It gathered resources, crafted new weapons and gear, It hunted, traveled, etc. So the GPT model, let's call it the Minecraft assistant, after reviewing its situation, would state the next action that it needed to do. Now remember that the way it integrated with the game was not by keyboard and mouse. It was using the API MindFlayer. This is code written in the JavaScript language that allows you to interact with the world. At the same time, there was another instance of GPT-4 that was tasked with creating the code. It was given the following prompt. You are a helpful assistant that writes MindFlayer JavaScript code to complete any Minecraft task specified by me. But who is me? So in this case, we have two models. Each one is prompted with helping me, but in this case, it's the other model. The assistant decides what to do, and the coding assistant creates the skill to make that happen. So if the Minecraft assistant wanted to go chop down a tree, the coding assistant would write the code to chop down the tree, and that code would be tested in the game. The bot would attempt to execute that command to see if it would work. If it didn't, there would be some type of environmental feedback, some execution errors. For example, here when it tries to create something called Acacia Axe, it would receive an error, there's no such thing. The text in green is its next attempt. As you can see, it calls it wooden axe, corrects the rest of the code, and now that script will work. So it coded up a new skill, corrected any bugs or errors, and made sure that that skill works, and then it adds it to its skill library. Next time that it meets that scenario where it needs that skill, it can just go into its skill library, pull it out, and use it. Over time, its skill library grows, and it becomes more and more adept at navigating the world of Minecraft and completing the various diverse tasks that it set out to achieve. So how well did this approach work? It turns out extremely well. Voyager did far better than the previous state-of-the-art model. It obtained 3.3 times more unique items, it traveled 2.3 times longer distances, and unlocked key tech tree milestones up to 15.3 times faster. As the researchers put it, Voyager shows strong in-context, lifelong learning capabilities. In-context learning capabilities means that it can learn on the fly, basically learning from the context of playing the game. And lifelong learning here means that it doesn't stop. It keeps getting incrementally better. Most previous models plateau at some point, but this one just kept going. This model is capable of improving itself, of teaching itself new skills, how to do something in the real world. But in a minute, I'll show you why the difference between playing a game and the real world might not be that big of a leap, at least for these AI models. Eureka. Now that same Nvidia team behind Voyager did not stop there. They decided to take that idea and apply it to something a bit more complex. In this case, teaching robots pen spinning tricks. Anima Anand Kumar, one of the researchers on this project, puts it, reinforcement learning has enabled impressive wins over the last decade. Yet many challenges still exist, such as reward design, which remains a trial and error process. Eureka is a first step towards developing new algorithms that integrate generative and reinforcement learning methods to solve hard tasks. So these reward functions are how we train robots to do the things that we want them to do. So for example, if we wanted to pick up an object and put it in a container, the reward function might give it points for successfully placing the item inside of the container and penalizing it for dropping the object outside of the container. It's a simple thing to write for some tasks. A model that's taught to recognize pictures of dogs might get a reward for getting it right and a penalty for getting it wrong. But how do you incentivize it to spin a pen? Writing these reward functions are notoriously difficult to do and sometimes pretty hilarious. For example, let's say that you want to train a humanoid shape to walk from point A to point B. The reinforcement learning process might teach the model how to get between those 2 points, but how it did it could be completely off. This is how I want to enter a room. But here's where Eureka comes in. Here's the function that it creates, for example. Notice that it has rewards for forward velocity. If it's moving forward, it's doing something right. It also rewards lower energy usage. The units of energy that are used to move get subtracted from the score. You're hopping everywhere you go, but it's just not the most efficient way to use your energy. There's also a penalty for putting a lot of force on the joints. or low impact is what they'd say in a fitness class. And of course, a penalty if it falls flat on its face. Now, how did it write this? Well, again, GPT-4 is at the center of this whole thing. These robots, hands, and humanoid puppets are trained in a simulation, but later that learning can be transferred into the real world. I think that's similar to the storyline of Gran Turismo, where a kid was playing a lot of video games, racing games, and they actually had him race real cars on a team. They actually did take him to be in a motorsports elite team. So this actually does happen in real life examples too. So this approach worked fairly well for creating capable robots. This approach tends to beat the results of having someone script the movements. So when you see footage of these little digital robotic hands stretching into infinity, that's the Isaac Gym. That's a simulation where these robots were trained, where they're given the reward function and they keep trying to get better and better at the task that they're learning. We give GPT-4 the environment code. This explains how Isaac Gym works. Then we give it the tasks it's supposed to do. Here, that's to make the shadow pen spin to a target orientation. But it could be to open a drawer or to balance a ball on a plate or those other humanoid running things. GPT-4 writes a reward function that it thinks it's going to work. That code, the reward functions, are then put into the GPU Accelerated Reinforcement Learning Simulation, aka Isaac Gym. And sometime after that, the results come out. And this is called the reward reflection. It lists the penalties and the success rates and is asked to analyze the results and come up with a new, improved reward function. This is one loop of iteration.
After multiple rounds of improving on its own code, Eureka outperforms human experts on 83% of the tasks. What's more, it really shines at the tasks that are hard for humans, creating new and innovative ways to approach the problem.
Nvidia hardware. The same people that automated Minecraft, then training robots, are the same people who are now tackling automated chip design. Dr. Jim Fan posted, "Something Nvidia is very interested in, automating the design of the next-gen GPUs. Someday we can take a vacation and Nvidia will still keep shipping new chips. Time to kickstart a self-bootstrapping exponential loop that iterates over both hardware and models." The goal is to develop an open source dataset for hardware code generation. Open source means it's going to be available to anyone to use, not just Nvidia. So it's going to be interesting to see the results. If they succeed, it could kick off a brand new innovation cycle in automated chip design. What does that all mean? So we just went through several examples of research that seems to indicate that we're approaching a time where we could see self-improving AI. So there was a paper out of Stanford back in 2022 called Self-Taught Reasoner, or STAR. STAR enables AI models to bootstrap themselves into higher levels of intelligence via iteratively creating their own training data. One of the authors of the paper, Noah Goodman, said, "This, in theory, could be used to get language models to transcend human-level intelligence." How many years do you think we have until we have self-improving AI? 5, 10, 15 years? Or is it never going to happen? Let me know in the comments. My name is Natalia. Please consider subscribing to my channel, and thank you for watching.